All right, welcome back, everyone. We are still in section 4.1, and we are going to continue that for the remainder of today. As a reminder, we left off the last video saying that we want to find the value of the limit as n approaches infinity of Rn, where Rn is, if I am given this function, f of x is equal to x squared, Rn is, in this case, the sum of the rectangles that I am approximating this area, the area of S, with. That is the area underneath the curve f of x is equal to x squared on the interval from 0 to 8. Okay? So let's do that. The base of each rectangle, if I let n be the number of rectangles that I divide that area into, the number of rectangles. Therefore, again, this notation indicates that I'm letting that number of rectangles approach infinity. So if I let n be the number of rectangles, then the base of each rectangle, if you remember, we're dividing this area up into rectangles like this. So I'm taking this interval 0 to 8 and I'm dividing it into n rectangles. Therefore, the base of each rectangle is that distance from 0 to 8, which is 8 minus 0, divided by n, which is the number of rectangles. So that's 8 over n. And that's consistent for every rectangle. Every rectangle has the same base. So we got that part. The height of each rectangle for n rectangles, we've calculated the heights of the rectangles for a set number of rectangles. We've calculated them for 4 rectangles or 8 rectangles. How about for just a general n rectangles? Well, I know that they are given by the function values. So it's given by f of that right endpoint, that right endpoint. And I could probably figure out an expression for the right endpoint. If you think about it this way, this is the interval from 0 to 8. Okay, this is 0, this is 8. And if I divide that up into n pieces, well, this first piece has a x coordinate of 8 over n. This next piece, well, if this is 8 over n, that's the base of the rectangle. This is another 8 over n. So this next piece will have an x coordinate of 8 over n times 2. This next piece will have an x coordinate of 8 over n times 3. So that's 3 8 over n's, etc. So let's see. How could we represent that? The height of the first rectangle would be 8 over n, or f of 8 over n, excuse me. The height of the next rectangle would be f of 8 over n times 2, f of 8 over n times 3, all the way to the nth rectangle. The height of that would be f of 8 over n times n. Okay? Well, I could do a little bit better than that. I have a specific function f here. So instead of writing f of 8 over n, I could write 8 over n squared. So let's do that. So those heights, again, will be 8 over n squared, 8 over n times 2 squared, We carry on in this manner until we get 8 over n times n squared. Okay? Well, that allows us to find an expression for Rn with some of the rectangles. It's the base of each rectangle, 8 over n, times the height. First one is 8 over n squared, 8 over n times 8 over n times 2 squares, plus 8 over n times 8 over n times 3 squared. And we carry on in this manner until we get to 8 over n times 8 over n times the nth rectangle squared. Well, this is an expression with, I don't know how many terms. It has n terms, but n is an unknown constant. So let's see if I can, now that I have an expression, write that in a more compact form. And I'm going to tell you this right now before we start. If I am given the sum of the first n squares, so 1 squared plus 2 squared plus 3 squared plus 4 squared, etc., all the way to, say, n squared, there's a compact form for that. I can find that sum by taking that number n times n plus 1 times 2n plus 1 over 6. I don't expect you to have known that prior to this. I don't expect you to know it for tests, but it's helpful for this particular problem. If you take discrete math later on in your college career, you might see that particular equation come up. But we're going to use it in a bit. Okay, so back to Rn. Rn I could write as, let's see, what's constant in this formula? There's an 8 and then 2 more 8s. An 8 and then an 8 squared in every term. There's also an n and an n squared in every term, so I could maybe factor that out. 8 times 8 squared is 8 cubed over n times n squared is n cubed. And then what's left if I factor that out? This first term, if I factor that out, I just get 1, which I could actually write as 1 squared, plus this next term, if I factor out the 8 over n and the 8 squared over n squared, I am left with 2 squared, plus the next term, I'm left with 3 squared, and it carries on in this manner until I get to that very last term. If I factor out 8 cubed over n cubed, I'm left with n squared. Well, now that we have factored it, I can notice that this term is the same as this term up here. It's the sum of the first n squares, so I can replace it with this compact form using that formula. So this is equal to 8 cubed over n cubed times that formula, n times n plus 1 times 2n plus 1, all of that over 6. And just as a reminder, the reason that I'm doing this is because I need to somehow apply the limits as n approaches infinity. And it's a lot easier if I can write it in a compact form in this particular case. So that's where I'm headed with this problem. Now that I have written it in a more compact form, let's see if we can simplify. Let's see if I have any terms that will cancel top and bottom. And let's see if I can rewrite it in a more helpful manner. Okay. So let's see. 8 cubed over n cubed times n plus 1 times 2n plus 1 over 6. Maybe I'm going to rewrite it so I have all those constant terms. written together and all the n terms written together, then it's a little bit easier to see. 2n plus 1 over n cubed. I can see that I have a single n term on top that cancels top and bottom. So there's that. 8 cubed over 6. What I'm left with in the denominator is n times n. And I'm going to rewrite this expression and make use of that. I could rewrite it as n plus 1 over n times 2n plus 1 over n. If you were to multiply two fractions like these again, you would get back to this because n times n is n squared. N plus 1 times 2n plus 1 is this term, this expression, excuse me. And why is that helpful to me? Well, notice that if I divide n by n, I get 1. If I divide 1 by n, I can write that as the expression 1 over n. So this is 8 cubed over 6 times 1 plus 1 over n times 2n over n is 2 plus 1 over n. Okay. So this is Rn. I've written it in a simpler manner. That is the sum of n rectangles on the interval 0 to 8 given the function x squared. Okay, so now that I've written it like that, I'm going to bring back the limit. The limit as n approaches infinity of Rn, which is what we were trying to find, is equal to the limit as n approaches infinity of 8 cubed over 6 times 1 plus 1 over n times 2 plus 1 over n, which is equal to that constant term I can bring out front, 8 cubed over 6 times, I can bring limits inside of the parentheses. I know the limit of a product is the same as the product of the limits, and the limit of a sum is the same as the sum of the limits. So I can essentially write this as 1 plus the limit as n approaches infinity of 1 over n times 2 plus the limit as n approaches infinity of 1 over n, because those are the only terms involving n, therefore they're the only terms affected by this limit. I know what this limit is. This limit is 0. Similarly, this limit is 0. So this expression becomes 8 cubed over 6 times 1 plus 0 times 2 plus 0, which, if you calculate that, you'll get 170 2/3, which is exactly the value that we were trying to get.